So now we pick up with describing sampling distributions. The fact that statistics from random samples have definite sampling distribution allows us to answer the question, how trustworthy is a statistic as an estimator of the parameter? Or how worthy is a sample to describe the population? So to get a complete answer, we consider center, spread, and shape. The center. If in the chips example, we collected many samples of size 20 with the red and blue chips and calculated the sample proportion of red chips. How well does the sample proportion estimate the true proportion of red chips? Remember, P, the population parameter, was 0.5. The center of the approximate sampling distribution is close to 0.5. In fact, if we took all possible samples of size 20 and found the mean of all those sample proportions, we'd get exactly 0.5. A statistic used to estimate a parameter is an unbiased estimator if the mean of its sampling distribution is equal to the true value of the parameter being estimated. So if the mean of the sampling distribution is equal to the population mean, then we can say that it's an unbiased estimator. For spread, low variability is better. To get a trustworthy estimate of an unknown population parameter, start by using a statistic that is an unbiased estimator. This ensures that you won't tend to overestimate or underestimate. Unfortunately, using an unbiased estimator doesn't guarantee that the value of your statistic will be close to the actual parameter value. Large samples have a clear advantage over smaller samples. They are much more likely to produce an estimate close to the true value of the parameter. This is labeled incorrectly, I believe. I believe the green one is n equals 10, and the red one is n equals 1,000. There are general rules for describing how the spread of a sampling distribution of a statistic decreases as the sample size increases. One important and surprising fact is that the variability of a statistic in repeated sampling does not depend very much on the size of the population. So the variability of the statistic, the standard deviation, is described by the spread of its sampling distribution. This spread is determined mainly by the size of the random sample. Larger samples give smaller spreads. The spread of the sampling distribution does not depend much on the size of the population, as long as the population is at least 10 times larger than the sample. Remember that 10% rule? We can think of the true value of the population parameter as the bullseye on a target, and of the sample statistic as an arrow fired at the target. Both bias and variability describe what happens when we take many shots at the target. So if you look at target A, it's high bias but low variability. All the dots are really close together so that it doesn't spread much, but it's not near the center. If you look at B, low bias, high variability, they're all roughly around the center, but they're very much spread out. Letter C represents high bias and high variability. They're spread out and they're not close to the center. Letter D is ideal. There's no bias and there's low variability. So bias means that our aim is off and we consistently miss the bullseye in the same direction. Our sample values do not center on the population value. High variability means that the repeated shots are widely scattered on the target. Repeated samples do not give very similar results. in this problem, it says, here are 4 additional methods for estimating the total number of tanks. This was the tank problem. I'm not sure if we ever went through and read that or not. You might need to go back and look at that. It's at the beginning of section 7.1. The partition method that was chosen by the mathematician is also included for comparison. Okay, so partition was equal to 5/4 of the maximum. The max, which was equal to the max, the highest one. Mean median is mean plus median. Sum of the quartiles is quartile 1 plus quartile 3. And number 5, twice the interquartile range. The graph below shows the approximate sampling distribution for each of these statistics when taking 250 samples of size 4 from the population of 242 tanks. So this is showing us a dot plot of all of these values using the tank information. So these right here, what they did to create all of the dots. So letter A says, which of these statistics appear to be biased estimators? Well, I hope you can look at this and see that max is definitely biased because it's skewed to the left. It's not at the center. And also, the other biased one looks to be twice the IQR. Also, it's this one skewed to the right, but it also has a lot more dots to the left. It doesn't surely show us a proper center with that center line. Of the unbiased estimators, I would look at the partition one. I think it definitely shows us the mean line, but or the total, it's hitting the mean because it's spread out, it's skewed to the left, but it still looks like this dark blue line is probably where the mean would be located. Of the unbiased estimators, which would be best? Well, looking at all of these, I'm looking at this and I would say that the sum and quartile ones looks to be about the same. It's pretty variable, but it's right there in the center. It looks like it's kind of a normal shape. And explain why a biased estimator might be preferred over an unbiased estimator. I'm not really sure how to answer that, so I'm going to go look at the book and I'll tell you what that says. Okay, so what the textbook is telling us is that even though the max is the biased estimator, so right here, it often produces estimates very close to the truth. Mean times median, although unbiased, is quite variable and not close to the true values as often. For example, in 120 of the 250 SRSs, max produced an estimate within 50 of the true value. However, mean plus median was this close only 79 of the 250 SRSs. I feel like they had more information to be able to answer that than we did. That concludes section 7.1, where really we're just kind of discussing the difference between a statistic and a parameter and how we're going to describe them.